We're starting the topic of electrical circuits by looking at the four main quantities that we'll be dealing with throughout the topic. You need to have an understanding of what's happening at a particle level for each of these in order to fully appreciate the full topic and how it links into other areas of the course. So I'm going to do a quick rundown of those four quantities to begin with and what their symbols are in the units. So we're beginning with current. We'll also be dealing with voltage. And those are our two most basic quantities. They're technically not fundamental, but for the GCSE course, they can be classified as that. And then we also deal with power and resistance, which are two derived quantities. So they actually stem from current and voltage. So the symbol for current is I, and it has the units of amps, and that would be capital A. Voltage is V, volts, and V. Power is P, which has the unit watts, capital W, and resistance is R, and carries the unit ohms, which has the Greek letter omega. Okay, so anytime you see these in a shortened equation, there'll be the symbols you see. Anytime you see data in a question, it'll be the units you see after the data. The final point on this slide is that we need to remember that watts are actually a measurement of energy, and it is the joules per second. So if you're dealing with a 60 watt bulb, for example, that bulb requires 60 joules of energy in the first second, then the next second, and every second as long as it's running. So taking a look at current, we need to have an understanding of what's happening at a particle level. So we're going to come from the perspective of a simple battery. Okay, now, any battery, or the most basic designs, are a simple metal rod encased and surrounded by a chemical. Okay, so that's all that's going on inside the battery. It's just a simple metal rod and a chemical. Now, obviously, that won't work with any metal and any chemical. They are designed to do a specific job. And the whole point of a battery is that when that metal rod and that chemical react, they produce an excess of electrons. Okay, so the metal rod will react with the chemical to produce another chemical, which is irrelevant because it just stays inside the battery, but it also produces what we refer to as an excess of electrons. And those electrons are built up and sit on the negative terminal of the battery. Okay, so we have the positive terminal and the negative terminal. The negative terminal is where those electrons sit. Now, the battery won't carry on doing that chemical reaction as long as those electrons are sat on the negative terminal. There's only so many can sit on the end of a battery before the chemical reaction stops. So for the battery to carry on reacting inside, we need to give those electrons an outlet. And we can do that by providing a wire with some sort of component, and for simplicity we'll go with a bulb, and then connecting around to the positive. Now, if there's enough electrons sat on that negative terminal, they will push their way through the wire, through the bulb, and all the way to the positive terminal, because the electrons being negative will want to be attracted to the positive terminal of the battery. And when we do that, all the electrons are moving in the same direction, and that is what we call a current. Okay, so they're all flowing around that circuit in the same fashion. And that is how we define current, or for GCSE, how we define it. It works for any charged particle. For GCSE, we're only dealing with electrons. So a definition of current is the flow of electrons. Okay, and if that crops up in an exam, that is worth a mark for that definition. So you need to know it. Now, voltage is a little trickier because the voltage actually changes as we move around the circuit. Again, we're coming at this from the perspective of the battery. So rather than doing a loop form of the circuit where the wire goes from one end of the battery all the way around to the other, we're going to come in from the perspective of if it was just a straight line. And so wire coming away, putting a cell in the middle, and then we're imagining this wire carrying on until it goes back to the other end of the battery, the positive side. Okay, so those 2 points there, call them both point A, they are the same point. So we've built up our excess of electrons on the negative terminal, and then we've built this complete circuit. So we know from our definition of current that those electrons are going to happily flow from one side of the circuit to the other. That's our definition of current. But in order to do that, they need the energy to push their way through the wire and any components in their way. And that's what the battery actually supplies. The battery is a supply of voltage. Now, we always refer to it as voltage for GCSE and for the majority of A level, but it's actually an incorrect term. It's what is known as potential. And the bigger the battery, or the stronger the battery, the more potential it supplies to those electrons and the more they can achieve. But the important thing is that when those electrons leave the negative terminal, that they are, for that particular circuit, high potential. And by the time they reach the far end of the circuit, they need to have zero potential. They need to offload all their potential along the route, kind of like a delivery service. If they reach the other end, the positive terminal of the battery with any potential left, that potential is then transferred to the battery, which will make it heat up and either split or catch fire or explode. So when circuits are built, they have to be designed to allow the electrons to lose all their potential along the route. And we can demonstrate this in a graph, showing what's happening as the electrons move across. And we're going to focus for voltage on what happens to an individual electron rather than all the electrons at the same time. So as that electron leaves the battery, its potential is high. It starts at a high point on the graph. And it'll move through the wire, losing next to no potential. Okay, we can take wires as being very easy for electrons to travel through, and therefore they don't use up any potential. It's not actually true, but for the purposes of this course, it does suit our purposes. When that electron then enters the bulb, it will lose its potential to the bulb. And by the time it leaves the bulb, it needs to have gotten rid of all of its potential. So that point there is where it enters. And by the time it leaves the bulb, it needs to have lost all of its potential and be down at zero potential for the rest of the journey. Now, that might imply that it no longer has any energy or potential left to travel through the last wire. And that is true, but it will keep going because it's not just one electron doing it. The electron behind it will push it forward, and the electron behind that will push that one when it has no potential. So it has kind of a domino effect that as more and more electrons travel into the bulb, the zero potential electrons can't just sit in the second wire. They have to get pushed further and further along that wire to get out of the way. Otherwise, we just end up with a huge excess of electrons inside the bulb, and anyone who touches that bulb will then get an electric shock. So it's that idea of potential that we need to focus on when we're thinking about voltage. Okay, and just to talk through another example, if we were looking at a battery that was connected to 3 bulbs, exactly the same thing would happen, but it would happen in more of a stepped fashion. Okay, so that's point A again, coming in by there to make it a complete loop. So again, as the electrons leave that battery, they start with high potential, and then when they get to the first bulb, they will use up some of the potential to get through that bulb. They then carry on through the wire, get to the next bulb and lose more potential. And then when they get to the third bulb, by the time they leave the third bulb, they need to be down to the bottom, no potential left, so they can safely return to the battery. Okay, so when we talk about voltage, what we're actually interested in is potential, or more specifically, because it's very difficult to measure what's going on with one electron, we measure what's called potential difference. We can't get hold of an electron traveling through a circuit because they're very difficult to isolate. So what we'd actually do is examine an electron at one point, and then we examine an electron at another point, and we look for the difference. And the difference between those 2 points will tell us what's happened in between. So if we looked at an electron at this point and it had 9 volts of potential, and then we re-examined that electron at this point, and we found that it only had 4 volts of potential, we therefore know that that battery must have received 5 volts, because that is the potential difference from one point to the next. This brings us to our first derived quantity of the 4, which is power. Now, I mentioned power earlier as being measured in watts, and watts being the same as the number of joules per second. And anytime we're talking about joules, we are referring to the energy, either the energy being produced or the energy being used by a system. The term per is no different to division, and seconds are obviously a measurement of time. So from that term joules per second, we know that we're dividing the total energy by the total time it's been taken to use it or to produce it. And that gives us our first equation for power. That power is equal to the total energy within a system divided by the total time it's taken to use that energy. Also gives us our definition of power. Now, anytime we're dividing by time, that gives us the word rate. So our definition of power is the rate of either use or production of energy. So obviously if the power coming out of a battery, it'd be the rate of energy produced. If it's the power going into a bulb, it'd be the rate of energy being used. As I mentioned earlier, so if we were talking about a 60-watt bulb, that would mean that we are using 60 joules of energy per second, every single second, as long as that bulb is on. However, that definition doesn't derive the quantity, doesn't link into our fundamental ideas of current and voltage. So we also need a second equation that links to those two ideas within circuits, because we're certainly not going to be able to measure the energy being used. We'd have to look at those fundamental quantities of current and voltage instead. So our second equation for power is that the power is equal to the voltage, or the potential difference, multiplied by the current. And it's essentially looking at how much energy is being delivered. That voltage can be considered to be the energy delivered per electron. And the current is the number of electrons. So obviously those two have an intrinsic influence over the total power. If you send more electrons out, there's going to be more and more deliveries being made to those components, and therefore it's getting more energy in total. If you increase the voltage instead, that would mean that every single electron would be carrying more stuff, more potential. So every electron that then goes through a light bulb would deliver a bigger dose of energy to that bulb, and therefore it's getting more energy every second. So it's very much a seesaw effect between these two, and we can decide how much voltage and current we're going to use to achieve the power we want. If we wanted more power, we could either increase the current and keep the voltage the same, or alternatively, we could keep the current the same and make those electrons carry a higher potential to produce more energy when it reaches the components. It's a little bit like if we had a delivery system, if we had a stack of textbooks in school that we needed to get to a classroom the other side of the school, we could either ask maybe 2 students to carry half of them each. So you'd have a small stack each, or, well, not a small stack, 15 books each, and they would take them. Alternatively, we could ask 15 students, well, I'm not going to draw 15, but we could ask more students to carry a smaller bundle each. We can stop the menu coming up. So in this scenario, we would have a low current and a high voltage. And in the other scenario, we'd have a much higher current because we'd have more students acting as our electrons, but they would all be carrying much less potential, much less books, so they'd be low voltage. Either scenario works because the books do end up at the other classroom. And when we're building circuits, what we have to decide is what is the most efficient way of transferring that energy. Sometimes it's by sending a lot of electrons, sometimes it's by having less electrons that have a higher potential for each electron. We reach our final quantity, which is resistance. Now, resistance, again, like power, is a derived quantity that links voltage and current. But it has an unfortunate effect. Whereas we want the voltage and the current to work together to produce a higher rate of energy, a higher power, resistance actually has a negative effect in most cases because it slows down the flow of current. So our starting point for this is our definition. It's any material that slows the rate of flow of current. So in a wire, electrons can move quite quickly. They have no issues. There's not a lot getting in their way. But then when it flows through other materials, there's a lot getting in the way of the electrons that slows them down. And when the electrons are slowed down, they need to offload their potential, and they do that in the form of heat. Okay, so this is why if you put particular materials inside circuits, they will heat up and catch fire. This is how a kettle will work. They actually choose to put a resistive material in there. So as the current tries to flow through it, it generates a huge amount of heat. But it's very expensive. And in most cases, we don't actually want to generate that heat. We don't want our mobile phones getting hot because we use them a lot. We don't want TVs getting hot because we're watching a long program. So resistance usually is considered a negative thing. So our definition of resistance is slowing the flow of current. And in order to calculate resistance, we use Ohm's law. Okay, so we can put Ohm's law into a triangle. We have V at the top and IR at the bottom. So one of the most common ways of writing Ohm's law is that the voltage is equal to the current times the resistance. Which when we rearrange to the, as I say, that is one of the common ways of writing it. The true form of that, because it's Ohm's law and it links to resistance, resistance comes first. And that resistance is equal to voltage divided by current. And that's what you'll see most of the time in your exam papers. Obviously, if you're doing higher tier, you'll need to be able to rearrange that at will in order to cope with what they want you to calculate. So to think about resistance in terms of particles, as I mentioned, we have electrons flowing through wires. So we're going to think of this in terms of the structure of a wire. Now, if the wire was just completely empty, like a water pipe, it wouldn't be a problem. Obviously in water pipes you do have a small amount of friction at the edges which will slow the water down and things like that, but on the whole the water will flow through the middle and won't encounter any problems that will slow it down. But that's not the case within wires. Wires are obviously solid materials, so they're made up of a lattice structure of metallic ions. Now, there's no escaping this because this is what makes electricity work. If we didn't have those positively charged ions of the metal inside the wire, we wouldn't have the free electrons that actually allows for electricity to conduct. So the problem and the usefulness of electricity go hand in hand. But what we have is when you have a current flowing, because the electrons carry a very, very small charge, you'll actually have a huge amount of electrons flowing through the wire at any one time. Now they're flowing because they're all going in the same direction, but that doesn't mean that they're all traveling exactly the same path. Some will be higher in the wire, and looking at it from a two-dimension, this is obviously a three-dimensional concept, but some will be higher up, some will be lower, some will be in the middle. And as they travel along the wire, some of them will actually collide with the ions of the metal. And the ion being much, much larger than the electron means that the ion isn't going to go anywhere. So that electron that hits it goes from a relatively high speed to a much lower speed. And therefore it's losing its energy. It hasn't got as much kinetic energy as it did have. So that energy, because it needs to be conserved, that energy is then transferred to the ion. But because the ion's massive, that doesn't mean that the ion shoots off, it just vibrates slightly. And as you'll see when we study conduction, whenever you have vibrating particles, that causes a process called conduction. And conduction is the transfer of heat through solids. So because these electrons are hitting the ions as they travel, they're losing a little bit of their energy, and therefore the wire is gaining that energy. The particles of the wire are vibrating, and therefore the wire starts to generate its own heat source and get warmer. Now, the warmer the wire gets, the less energy the electrons have to deliver when they get to their actual destination. So there are a couple of things that affect resistance. Obviously, the type of material will. There are some that are more conductive than others. So our choice of material is important. We want conductive materials in our circuits. But the length of the wire, as that increases, these electrons need to get past more ions, and therefore there's more collisions going to take place and more energy loss. So as the length increases, resistance will increase, and therefore heat loss increases. The other aspect we can look at is the diameter or the width of the wire. Now, the bigger the tube or the wire for the electrons to flow down, the more space there will be. It's no different thinking about a road system. Obviously, if you're traveling on a motorway, you can fit a hell of a lot more cars on a motorway than you can on a country road. So if you took all the cars off the M4 and channeled them down a narrow road, there's going to be too many cars, they're all going to get in each other's way, and everything's going to grind to a halt. That's the same in a circuit. If we took all of these electrons and put them in a narrow wire, there'd be a lot more collisions, a lot more slowing down, and a lot more heat generated. So the wider the wire, the better. So as we said, as length goes up, resistance goes up, and heat loss goes up. But if we use thicker wires, so the diameter increases, the resistance actually drops, and the heat loss drops as well. However, this has the downside that obviously the bigger the diameter you have, the more material you're using, and the heavier those wires are going to get, and the more space they require. So again, it's very much when you're designing circuits, a balancing act of cost over the space. It'd be great to design your mobile phone that it didn't generate any heat, but it'd be about 10 times larger than it currently is, and therefore wouldn't be as effective or as useful as our mobile phones are now. So to summarize these four quantities, you need to know that when we're talking about current, we are referring to all the electrons moving around the circuit. When we're talking about voltage, we need to consider just what a single electron is doing. And obviously all the other electrons would replicate what that individual one does. Okay, so when we're thinking about voltage, think about an individual. Now we mentioned power as being the product combination of voltage and current, and also resistance being voltage divided by current. But I just want you to finally consider how those last two things actually work together. The power that's being delivered to a component fitting together with the resistance of that component. And to do that, we're going to revisit that idea of potential difference and our stretched circuit as the electrons flow through a circuit and return to the opposite side of the battery. So once again, we're thinking of the negative terminal of the battery and a wire going to, we'll do 2 bulbs this time, and then flowing back to the positive side of that same battery. Now we mentioned earlier, when we're thinking about the potential and how that changes through a graph, through the circuit, that the electrons, so the current leaving the negative terminal, will start with a high potential. So at the very beginning of the circuit, they have a high potential and they travel quite nicely through the wire. And that then when they enter the bulb, they would start losing potential until they reach the other side of that bulb. Now, linking this in with our other quantities, that would mean then that that bulb is that electron is losing potential, and the bulb itself is gaining that energy to function as a light bulb. So therefore, that bulb needs to have higher resistance. It's the resistance and the way we build the bulb that allows it to take that energy from the electrons that were quite happily flowing through the wire, generating very little heat. So if you look at the structure of the bulb, it is designed to steal the potential by creating more and more collisions. And if you used to hold up a classic kind of Edison bulb, that is the design that we have. You have a very narrow filament in the middle, and it's the fact that that filament is so much narrower than the wires going into the bulb that generates that heat. It links back to that idea of if these were the motorway where all the electrons can travel pretty happily, and then we feed all the cars from the motorway into a tiny, tiny country lane, there's going to be a lot of collisions and a lot of slowing down, and therefore a lot of heat generated. So because of that resistance, the electrons are losing potential, and therefore the bulb itself is technically gaining that potential, which is then exhibited as the power of that bulb, the light that's given off. Then when those electrons leave, they can travel through the next wire pretty happily till they reach the second bulb, and then the second bulb will steal more of their potential in order to generate the heat that causes that bulb to light up. Okay, so these quantities are not standalone, they actually function together. Okay, and a lot of the time we do require the resistance in order to steal the potential and therefore the power from that circuit to make those components actually function. So your task from this lesson then, I'm going to attach some equation worksheets for you to have a look at that, look at power and resistance with their simple form of equation. Okay, so we have the 3 equations for you to be considering. The first one being that power equals energy divided by time. And make sure that you're working in the right quantities for this. The energy has to be in joules, the time has to be in seconds, and that would generate a power that was measured in watts. Obviously, if you were rearranging that, you'd have to be able to do so yourself for higher tier. And if you were calculating either the energy or the time, they might give you the power in kilowatts. So you have to be able to do conversions for kilo and mega and giga and everything else. So our triangle for that, P would go at the bottom. We'd have E for energy at the top because it has to be above the T for time. Our second equation is our power equation linked to voltage and current. So voltage times current, where again power is measured in watts, voltage is measured in volts, and current is measured in amps. We'll re-emphasize at this point that if they're doing shorthand versions of current, that would be I for the symbol. So you might see things like I equals 12 amps. Okay, the amps should tell you it's current, but also the symbol I should tell you that it's current as well. Obviously, the others are fairly straightforward because it's just the first letter of the term. So putting that into a triangle, you'd have power at the top because voltage and current have to be side by side to be multiplied. And then our last one, we have resistance being equal to voltage divided by current. So again, you're more than welcome to use the triangles if you're doing foundation, but if you're doing high, you should be able to rearrange this yourself. So you have R at the bottom because V has to go at the top in order to be above current. So I'll attach those worksheets and let me know if you have any problems with them.
Hello.
Hello.